This is an FOA hands-on hints video using an OTDR. Let's take a look at a current generation portable OTDR, get a bit of an idea of how it works and how we can get the best results from it. If you've watched the FOA lectures 17, 18, and 19 on OTDRs, you know that OTDRs work from one end of the cable and create a snapshot of the cable. We can operate with a single launch cable into the cable under test and get some information, or add a receive cable on the far end and get information on the loss of the connector on the far end. The OTDR gives us lots of information in the trace. The slope of the trace shows the fiber attenuation coefficient. The connector loss is shown by a drop at a connector, which typically is a reflective event, and that also allows the OTDR to measure the reflectance. Splice losses are usually not reflective events, but the OTDR can measure the splice loss by looking at the drop in power across the event. There's lots of information here if we know how to use it properly. We have here one of the new small handheld OTDRs, this one from Advanced Fiber Solutions in Boston. We have a launch cable, 150 meters of single mode fiber provided by FiberNext, and a box with a short cable plant in it, which we can use for evaluation of the OTDR. So let's fire up the OTDR and take a look at it. The OTDR boots up in a few seconds and gives us the choice of doing a setup and running our own tests or doing auto test. So let's hit auto test and see what it can do. In auto test, the OTDR chooses its own parameters, takes a trace, analyzes it, and gives us the results. It only takes a few seconds, and there we are. There's our trace. But we know we only have a 150 meter launch cable and 1 kilometer of fiber. That trace shows a lot of ghosts and a lot of noise. I think we can do better. Let's see. Well, the auto test shows 1300 nanometers, a 5 kilometer range, and a 25 nanosecond pulse width with a 5-second measurement time. Well, let's see what we can do. Let's change the distance we're looking at to 2 kilometers, which is about twice as far as the actual cable we've got. Let's change the pulse width to 6 nanoseconds, which is the shortest we've got, which should be fine on a 1 kilometer link. And let's change the measurement time to 15 seconds, which will reduce the noise a little bit. We'll save that, and now let's run the trace again. Take us about 15 seconds. Here's a sample of our trace, zoomed in, to show how cleanly we can get the trace if we set the parameters correctly. As you look across the trace, you can see our 150 meter launch cable and our 1 kilometer of fiber that we're testing. And at the end of the 1 kilometer, it drops down into the noise. This is how a clean OTDR trace should look, and a trace that the OTDR can analyze properly. How did we manage to get such a cleaner trace? Well, one thing was most important in doing that. When the OTDR chose its own parameters for an auto test, it chose a 25 nanosecond wide test pulse. That's probably not a bad idea for auto test because you don't know if the cable's 1 meter long or 20 kilometers long. But it's certainly not optimal for our 1 kilometer cable. There's a lot of excess energy in that pulse, and that's part of what causes all the ghosts we saw in the trace that the OTDR gave us at first. When we reset the parameters, we went to a 6 nanosecond wide pulse, the narrowest available to us. That maximizes the resolution of the OTDR, which is important when measuring short cables. And it also reduces the amount of energy in the pulse, which is reducing the ghosting that we saw in the original trace. This is why, when you know the cable plant you're testing, you can go in and choose parameters in the setup that are optimum for that cable. Here you can actually see the same trace taken with 4 different pulse widths. On the lower left-hand side was the 25 nanosecond pulse that was chosen by the auto test. On the lower right side is a 100 nanosecond wide pulse, which is appropriate for very long cable plants. There's also a 12 nanosecond pulse in the upper right-hand corner, and the 6 nanosecond pulse in the upper left-hand corner we chose for our test. By choosing the appropriate pulse width, you can get the best resolution and distance trade-offs on every trace. But you need to know how long the cable plant is and how the OTDR trace will be affected by the pulse width in order to make the right choice. Here's what happens when you test with that wider 25 nanosecond test pulse. You can see the red arrows pointing to all the ghosts in the trace. The ghosts are offset from the actual traces by the same distance as they are in actual length. So you can see the far left arrow points to the first ghost, which is from the 150 meter launch cable. You can see a second version of that ghost, and then a ghost of the 1 kilometer cable, and yet another ghost of the 150 meter cable right in the center of the trace. This is a common occurrence when you use too high-powered a test pulse. Here's the same trace taken with a narrower pulse width, and you can see how it reduces the ghosting tremendously. Choosing the right pulse width is always important to make sure that you're analyzing the trace properly. One of the most helpful things to have when you're trying to test a cable plant with an OTDR is to have documentation on the cable plant. That documentation should tell you how long the cable plant is and where to expect events like splices and connectors. It will help you set the OTDR parameters to best view the fiber. Once you've taken traces and analyzed them manually and know that the OTDR can do the traces properly, you can then try using AutoTest and determine whether or not the OTDR can use AutoTest on other fibers in the same cable, which can, in fact, save you a lot of time. But it doesn't save you any effort unless they make proper measurements, and only you can determine that by manual analysis of the traces. The FOA has several other YouTube videos on our YouTube channel covering OTDRs, how to set them up, and how to use them. We also have extensive material in our online guide on OTDRs that covers the same material in even more detail. Feel free to use all this material to help advance your knowledge of how to test fiber optics correctly. We're the Fiber Optic Association, the professional society of fiber optics.